Hi there, everyone. I hope this video finds you doing well. Before I jump in, and especially since we're moving on to a new chapter today, I want to remind you the test coming up on Thursday. I've been calling it test 2, but you may also be thinking of it as mini exam 1. So I apologize if there's confusing terminology. Note that this new material from chapter 14 will not be on the test this week. Only the content through the end of chapter 13. If you have a specific question, let me know, but I did send out an announcement highlighting the content that will be on the test. And I will also put together a set of practice problems for you. But with that being said, let's jump in and look at chapter 14. And what we have here is a continuation of the ideas that we discussed in chapter 13. We are still going to be looking at sampling distributions, but now we're going to be extending the concept, and rather than looking at the sample distribution of a sample proportion, we're going to look at the sample distribution of a sample mean and how that is connected to an important result in statistics that we call the central limit theorem. Now, the easiest way to get at the concept that we're discussing today is to revisit a data set that we talked about at the start of chapter 13. There, we were looking at the proportion of babies born that were underweight at birth. But let's say we're not interested in a proportion per se. Let's say we're just interested in the average birth weight. So this data set that we discussed from 1998, it looked at all babies born in the US that year, nearly 4 million of them. And the histogram you see on the screen shows you the distribution of all birth weights. You'll see, it looks close to symmetric. It is a little bit skewed to the left. You can see the tail of the histogram to the left is definitely longer than the tail going to the right. But this histogram, it represents every single birth weight from the year 1998. And birth weights are a quantitative variable. In this instance specifically, we're looking at birth weight measured in grams. Now, this situation from 1998 is kind of idealized because typically we won't be able to do a census of all births. What we may be able to do is, through a good sample design, we may be able to sample 100 randomly selected births from a given year and calculate the average. So what would happen if we could do that? Well, we're going to do the same thought experiment and say we can take this population and we can repeatedly take samples from this population. So let's say I do this 2,000 times, right? I take a sample of 100 birth weights from this year, and each time I calculate the sample mean, and I do that 2,000 times. What I have on this histogram now is the sample means of samples of size 100 for 2,000 different samples. And what you should notice firstly is this distribution is now a lot more symmetric. It's also a lot more concentrated. I'm going to scroll back up to this previous slide, and you'll see here, if we were looking just at individual birth weights, right? This one is for all individuals. It ranges from 125 grams to a little over 5,000 grams. Where if we take 100 randomly selected babies and we average their birth weight, now we have a much smaller span of values, like 3,150 through about 3,500 grams. So what happens when we take the average, if we look at this new histogram, is it has a much smaller standard deviation, evidenced by how much narrower the spread of the histogram is. The full population, the one on the previous slide, had a standard deviation of nearly 610 grams, but here our standard deviation is much closer to 61 grams. But the other thing that's interesting is if you take the average in the population and you take the average of the sampling distribution, those numbers are nearly identical. So the sample mean distribution has a mean that's very close to the full distribution of all individuals, but it has a standard deviation that's a lot smaller. And I realize that just that whole sentence can probably sound a bit confusing. So if you bear with me for a moment, we will unpack that a little bit more in 2 slides. What I mainly want to make sure of first is that everyone understands where I got this green histogram from. So let's talk through this conceptually one more time. How did I construct this new histogram? Well, I took my population, all the birth weights from 1998, and we know there were nearly roughly 4 million of them. So I sampled 100 babies from that population. And for that sample of 100 babies, I calculated the mean for that sample, or that sample average. And I repeated this 2,000 times. So each time I took a new sample, calculated the sample average, and I did that 2,000 times. And those sample means or sample averages, that's what I then put in a histogram. So this is what we call the sampling distribution of the sample mean. It shows us what we would expect to see for a sample mean if we could repeatedly take different samples from the population. Because remember, each time that you take a sample from a population, even if the sample is the exact same size, in this case, size 100, it's going to give a slightly different result. So we're able to construct here a histogram that shows us how much variation we're going to see in sample averages. And the bottom line is the sample averages vary a whole lot less than just individual observations. So this result, this kind of bell curve that we end up seeing and the reduction in variability, this is connected to an important statistical result known as the central limit theorem. What the central limit theorem tells us is if you are calculating the sampling distribution of any mean, so the quantity you're interested in is the sample mean or the sample average. If you want to know what that distribution looks like, the sample distribution becomes normal. The larger your sample size is, or as your sample size grows, the sampling distribution becomes more and more normal. And again, I'm going to show you another illustration of this concept in a minute. But let's talk about when the central limit theorem applies. There are a few requirements. Firstly, we need to have independent observations. So you need to know that you're not like sampling triplets and including all of those in your sample. Each individual sample needs to be independent of every other individual sampled. And you also need to make sure that you have randomization. There needs to be a random aspect to how the data are collected. If that is true, then as long as your sample size is large enough, or if you started with a population that looked very normal to begin with, if one of those things is true, then the sampling distribution of the means will be close to normal. So if you are interested in making a statement about a sample mean, then you will want to check if the central limit theorem applies. So you need to verify or state your assumptions regarding independence and random selection. And then you also need to look at the shape of your original population. Is the original population close to normal? And if not, you want to check your sample size and ask yourself, is your sample size large? Now, we will delve into this a little bit more. This is not the answer to every single problem, but we will, at least in this class, say that if your sample size is at least 30, we will consider that large enough. And I'm going to emphasize here, for this class. So this is not the result that you should leave here with and think this is always true in the real world. We are setting a threshold for application in this class, but that doesn't mean that it's a number that will always work in the real world. You always have to carefully look at your population, carefully evaluate whether your sample size makes sense. And if you feel good about those two things, you can invoke the central limit theorem. So I promised I would illustrate this to you a little bit more. Here in our right top corner, I have an illustration of a population, a very skewed population. You'll look at this histogram and you'll see it is not symmetric at all. It is skewed to the right, and it has this high mode at the very left end of the distribution. Now, conceptually, if this is your population and you start taking samples from it, and you calculate the sample mean for each sample, what do your sampling distributions look like? Well, that's what's being illustrated by these 4 different histograms. So let's look at them in order. If we're looking at the top left one, where we take samples of size 10, so this represents a histogram of sample averages or sample means, where we took samples from this very skewed distribution in the top right corner. You'll see it already looks a little bit more symmetric than the population, but there's still plenty of skewness. Top right quadrant, if we increase our sample size to 50, again, a little bit more symmetric, but still a tail to the right. But now when we get to sample size of 100 or a sample size of 200, both of those histograms look really nicely symmetric. So the example illustrated here is really an extreme case, because even at 50, the bell curve isn't all that evident. But most of the time when you get to sample sizes of 100 or 200, definitely you can feel pretty confident that you can justify the use of the central limit theorem, because you can see here we're getting very nice bell curve approximations here. Now, what the central limit theorem tells us, if we state it more formally, I know there's a lot of text to go through on this slide. It tells us if we start with a population that has a mean of mu and a standard deviation of sigma, and from that population we now take a sample and we calculate the mean of that sample, y bar. Then if we look at the sampling distribution of the sample mean, it is going to still have a mean of mu, and it's going to have a standard deviation given by this quantity sigma over square root of n. That we also refer to as the standard deviation of the sample average. So we sometimes denote it sigma of y bar, or we call it SD of y bar. But if you're working with a sample mean y bar, then you should remember that quantity follows a distribution that has a mean of mu and a standard deviation of sigma over square root n. Now, this does not depend on what kind of underlying distribution you have. Those two results will always be true, a mean of mu and a standard deviation of sigma over square root of n. But the approximate normality, that you need a large enough sample size for. So it tells you that that sampling distribution will follow a bell curve pretty nicely as long as your sample size is large enough. And large enough, at least for the purpose of this class, we'll say is at least 30 observations. So here's what that normal model now looks like. The bell curve here, this is a representation of the sampling distribution of the sample mean, y bar. And it shows you y bar follows a bell curve centered at mu, that's the mean, and then we said it has a standard deviation of sigma over square root of n, so that tells us how big these increments are on our normal bell curve. Each one is a jump that's of size sigma over square root of n. Now, we will say that in general, this quantity sigma is not known. Sigma is the population standard deviation. But what we can calculate is S, our sample standard deviation. And if you're able to calculate that, then instead of calculating standard deviation, you can calculate standard error. And standard error, or sometimes we'll emphasize standard error of the sample average, is given by S over square root of n. So it just takes the standard deviation formula and it replaces the sigma, the unknown population quantity, by S, the sample approximation of that quantity. Now, the normal approximation will depend to some extent on how large your sample is. In large samples, it's going to be very accurate. If you're in a small sample situation, you have to be more cautious about trying to use normality. So let's dig into that a little bit more. We're heading into subsection 14.2, and we will briefly touch on a formula for a confidence interval, but mostly I want to talk about this idea of when is the sampling distribution normal. So we get to talk about beer. Yay. There was a brewer who worked for Guinness, last name Gossett. And while Gossett was working for Guinness, he found that the normal model was not quite right. He tried using the bell curve to model some quantities related to beer and really found that some of those calculations ended up not being very accurate. He was still observing empirically that he was dealing with something bell-shaped, but the way that distribution looked depended a lot on what the sample size n was. And so he came up with what today is known as student's t-distribution. Now, student's t-distribution is a different bell curve than the normal distribution. And if you look at this graph comparing the two, what you'll see is that the t-distribution, it has what I'll call fatter tails. When you go out into the tail of the bell curve, the tails are a little bit thicker for the t-distribution relative to the normal distribution. So you are more likely to have very large positive or very large negative values with a t-distribution than with a normal distribution. And Gossett found that when he was working with the sample mean, if the sample size was small, he couldn't rely on the normal distribution. He had to use student's t-distribution for those calculations. So When certain assumptions are met, and if you want to know what these assumptions are, come back next week. Spoiler alert, we'll dig into those. But when certain assumptions and conditions are met, we can calculate something known as a t-statistic. The t-statistic takes your sample average, subtracts the population mean, and then divides by the standard error. This should be reminiscent of a z-statistic, but the formula is slightly different because it relies on standard error, not on standard deviation. Well, what Gossip found is if he calculated this t-statistic, then that quantity was related to the student's t-model with what I'm going to call n-1 degrees of freedom. So we'll really dig in next time and talk about what the degrees of freedom mean. But for now, it's important to know degrees of freedom are related to sample size. So if you have a sample size of n, then your degrees of freedom will be sample size -1. And it may be helpful to remember, this is also how we calculate our standard deviation. If you're calculating the sample standard deviation, you end up dividing by n-1. So the degrees of freedom here correspond to a quantity that shows up in the formula for sample standard deviation. Now, you will calculate your degrees of freedom, and that gives you a way of now again constructing a confidence interval. But the last time we talked about confidence intervals, we were doing them for a sample proportion. Now we're going to construct a confidence interval for a population mean. And the formula for doing that is given by our average, sample average, plus or minus, and instead of a z-star value, we have a t-star value with n-1 degrees of freedom multiplied by the standard error of the sample average. And we are really going to dig in next time and look at how to calculate this confidence interval. But it depends on a few things. It depends on the critical value, which is now a t-star instead of a z-star. And the way we find that critical value, it requires two different quantities. It requires knowing the confidence level, the C% that we specify for a specific confidence interval, and it also requires knowing the degrees of freedom n-1. Again, I know I'm covering a lot of theory ground, so we will spend ample time looking at illustrations and examples of this. But this slide is kind of the central numeric result for today. If you have two takeaways from today, one of them is understanding the central limit theorem. The other takeaway is the formula for this confidence interval. And I will illustrate to you next time how we do calculations relative to that. So having put central limit theorem and confidence interval formulas in your head, I'm going to stop here. We're not quite done with section 14.2. We'll pick up with that next class, but we will be doing some examples relating to this in our live Zoom session tomorrow. So I will talk to all of you then.